21, aren't you?
Yeah. I was drinking the whole time.
Yeah, you drink for free if you're gambling.
We did a lot of other stuff.
I didn't know about that.
I would.
I'm still upset we did not go see the Cirque du Soleil show. But,
Yeah.
you know, when a girlfriend's puking her guts out every 5 minutes.
Probably not going to happen.
No. And I wasn't a shitty enough boyfriend just to leave her and do that by herself.
It probably involved just, okay, well, bye, I'm going. Have fun.
Still hurts that we lost $180 there, but.
No, that's why you got to gamble with that.
So, what is your opinion about the subject of this meeting?
What is today's meeting subject?
Yes, can you guess?
VASP.
No?
That's tomorrow.
DFT?
Huh?
DFT?
Yeah, it's very general. We have the whole chapter on DFT. Some of you are already exposed to DFT practice and literature, and you may develop a guess what could be steps towards learning. No, we already mentioned them.
Functionals?
It will be on April 3rd or whatever, first day of first class of April. I will be on MRS conference in Phoenix, but I will try to broadcast it. Yes, there will be functions. And other guesses?
Light matter interaction?
Huh?
Light and matter interaction?
You missed it. It was when you were on physical society meeting. But if you are done with homework, you got it.
No clue how to use that.
No, not for us. Just for question number 1, number 2, the questions. Okay, so day of questions and answers. Any more guesses?
I have another question.
Yes, please.
Are we going to go over the modify electronic configuration tomorrow on that?
Yes.
Okay.
And we can leave most challenging questions to those who are not here to reward them. Any more guesses?
Density of space.
No, this is too applied. Something fundamental.
What's good? Wait, transitions?
No.
Com-sham orbitals?
No, it's too easy.
Spin polarization?
The Hohenberg-Kohn theorem?
Yes.
I was about to say
You
that
didn't
math
waste time
papers.
in your primary school when you learned how to read. So, we are looking on 2 meetings in front of us, which you will most likely never use in your life. So you just lean back, fall asleep, it's fine. But I will feel bad if I do not pronounce it. I want to have my self-consciousness clean that I deliver. So the next 2 meetings will answer on the question why density functional works. And this is more mathematical question. It is not a description of materials or modeling any specific molecule. As you may have heard, seen, and presented yourself, I know that I can make it darker, but I'm not sure if I can make it brighter. Okay, whatever. So, what did we do before? How did we set up computational chemistry problems or main task of computational chemistry? Main procedure. The theories and atomic coordinates in, observables out, right? And in the middle, one was finding the wave functions. And the main challenge that we did address is that wave function did have too many independent variables. All positions of atoms, all positions of electrons, and then it is unsolved. It's like function of 1,000 variables. Right? And then we went through Hardy-Fock theory. Well, we did Born-Hammer separation to get away from nuclear coordinates, and we did Hardy-Fock theory to solve self-consistent equations only for one fictitious orbital, assuming that it is such orbital that carries influence of all other occupied orbitals, right? You're not going to object. Thank you. But anyway, it is an approximate. Is an approximate theory, right? Generally, the paradigm is that you have truly multi-dimensional, many electron function, wave function. And out of such multi-electron function, you do find observable that your experimental friends that you want to report to the community. What is this function theory? It is theory of density, so that total energy is functional of it. Yep. Just make equilibristics with words. So the original idea was that we're somewhere here. Next coming Thursday will be another senseless theorem. Oh, very useful theorem. And in one Thursday later, and operating glass. And very soon we will do projects. I will make a special lecture with overview of possible projects. It's just one of them. Lipid by layer interfacing semiconductor. Yeah, this was density matrices for Hardy-Fock. I'll return to today's functional theory. I'll quickly recall for myself what were we doing before. And for those who were busy traveling, maybe it will be not completely loss of time. So this is our favorite Hardy-Fock, and we missed the concept of density matrix, which converts two electron integrals into Fock matrix. From here are integrals in atomic basis, and here this density matrix carries information about occupied orbitals and their decomposition over atomic orbit. And then you diagonalize Fock matrix, construct total energy, and repeat it again. If you drop electron-electron interaction, you get theorem named by economy prize holder, whose name, according to Christian, was
the economics guy.
name.
I can't remember right now.
First letter.
Wasn't that like a K?
Yes. Coupon.
Yeah, that's it.
Then we went through observables for light interaction, where interaction with light in dipole approximation is just subtracting dipole times Q from Hamiltonian. And then we generalized it to all many electrons, many ions. And then we found expectation value of this transition dipole in basis of multi-electron wave function, where initial state is when everything occupied, final state is one occupied. For example, home is promoted to another unoccupied. And when we practiced this multi-electron matrix element, we found that instead of multi-electron calculation, one can simplify this multi-electron procedure to much simpler, which is based on orthogonality, much simpler expression that is called transition dipole matrix element. And although we are looking for object localization from ground state to excited state, which both are multi-electron, this can be reduced to matrix element of one electron orbital. Right? I need to collect homeworks, otherwise you can just copy. It's answer on the question 1 or question 2, right? Those who show me a sign, they probably were just starting to do homeworks. Right? So original orbital from electron is taken from, final orbital where is placed, the position greater, and then integration. So it is, and there is a vector for that. Initial, final, and vector. Periodic. So VASP is needed because we need periodic materials, right? And then there are simulation cells which are replicas of each other. And then if potentials are repetitions of each other, the wave functions according to Helix block are also repetition to each other times phase factor. And phase factor is same as plane wave. So it's like if all electrons are sitting in their nests, but they're accumulating phase by moving this constant velocity across the whole infinite solid. This is what you just voted on, right? Okay, so it is where I have started to mumble. Wave function, total energy. So there is a hypothesis that wave function is boring and has excessively much information, that one can get observables based on knowledge only on charge density, which is a function like number of electrons per infinitesimal volume, point of space, in vicinity of point of space. This sounds and looks very appetizing. You already know that it works, at least qualitatively, but when this hypothesis was offered to the community, it was not accepted by everyone. And therefore people were designing theorems to prove it logical. So it is not just fantasy, but there is a straight mathematical proof behind it. And although I am not biggest supporter of formal logic and math, I will try to do my best just to tell how I interpret it. And if you do not trust me, you can just do it as a second opinion. Or maybe my opinion is second, this one is first. And we didn't start to do anything yet. It's review of what was on the past meetings. So, what is density? Some of you, I will not tell who, was asking a question. I was confused because of the semantics, because of the different concepts under the same word. So we all are finding density of states, right? Density of energies of orbitals per interval of energy. But now we are talking density of electrons in a sense of buoyance, of Archimedes, of like amount of mass per unit of volume or amount of charge per unit of volume. Those are different concepts, although we use the word density for both of them. And there is a very simple equation for this density and definition of functional, but I will skip it and I will probably invite someone to the board to draw it in a couple of minutes. So another piece of recalling from very last meeting. Give me signs if you are not comfortable with general common sense of the density functional theory and its main goal. You're not objecting. You agree that it is a noble goal to get total energy for cheap, right? Okay. So this goal was kind of achieved 20 years ago, 1 year after Schrödinger equation was derived. So how to get total energy of universe if the universe doesn't have ions, only electrons, and these electrons do not interact with each other. So it's density functional theory for free electron gas, and especially if you are in physics community or educational track, you will hear the abbreviation Thomas Fermi theory. Did you? Okay, some of you did. Then I do not need to be in much details. So you split all universe on cubes. Each cube is considered as particle in the box. For each particle in the box, you can make a space of eigenstates based on quantum numbers. Right? How many quantum numbers? Okay. Momentum in X, Y, and Z. And then in this space of quantum numbers, you can set up the radius, so that you browse in this three-dimensional space and select this radius, which, by the way, is connected to energy. And then by drawing spheres and shells in the space of quantum numbers, you can find density of states. And after you get number of states, density of states, and then you can derive expressions for number of Fermi energy and total energy. If you just play with this concepts and this expression for density of states for the system, you remember, right? Number of electrons and total energy, both as function of Fermi energy, which is just a border between occupied and unoccupied. Give me signs if you are not comfortable. Then, if you do have number of electrons as function of Fermi energy, you can invert and get Fermi energy as function of number of electrons in the box. Okay? And then you have two compounds. First, Fermi energy as function of number of electrons, and second, energy of all electrons inside your box of choice as function of Fermi energy. You combine these two, plug one into another, and then you have total energy of one box as function of number of electrons stored there, assuming that they are quantized but not interactive, and they just take this lowest, they occupy all available states of three-dimensional particle in the box. Okay, and then you play a little bit of math to multiply and divide by size of the box, number of electrons per size of the box, and then you come to the idea that total energy of electrons in the box is a function of density of electrons inside the box. Okay? And if you have many boxes, you just add them together, or if they are very small, you just integrate. So this power 5/3 is derived based on your knowledge on about particle in the box. There should be index TF for Thomas and Fermi. All constants are here in combined in Fermi constant, and it is one of the examples of density functional theory. It's not practical. We cannot describe molecules because all molecules have ions. But in fact, it is total energy as a functional of density, right? And it is local. It depends. This integration depends only on density, integration of density in the vicinity. You do not compare densities in the nearby points. Right? So it's local density. Well, it is not local density approximation in the rigorous sense, but it is very, very close. So this is ancient density functional theory, When it was designed, no one used the word density function. It is just atmospheric theory or electron gas. But this philosophy goes forward to modern era of computers, when one can add things here and there, like ions and electron-electron interaction, put positions of your carbons or lead or whatever ions to molecule, and get total energies in a very reliable way. Not super precise, but much quicker than most of other methods of the same precision. Make sense? More or less? Okay, and there was nothing new yet. If you were attending, you heard it. If you were not attending, you may have watched it online or through recorded notes. Okay, so after I see your choices, I will probably decorate it so that it will be a list of presentations on next Thursday. And we are going to learn background concepts of density function theory with the following purpose. The amount of computational chemists or electronic structure calculation people is much less than amount of experimental researchers, maybe 10% or 5%. And amount of people who not just use theories but design them is much smaller fraction of those who does calculations. So based on this statistics, like maybe less than 1% of scientists do theory, it's very likely that no one of us will design theories. But we need to be aware of them, and when you will do the calculations, you need to be just specific about which equations are being solved. Some of the, if your papers will come to revision to theorists, and you just mention, I use this software, I choose this base set. Okay, another experimentalist who just got Gaussian license. You need to tell it, here is the equation. Doesn't matter which software, we found a way to solve it numerically. So it is, it will go much easier for explaining what you are doing in the theoretical computation community. So this is a little minor practical benefit of listening this. And taken or not taken notes. So the plan, background, done. Definitions, almost done. Theorems, there are 2 of them, 1 per lecture. So 1 today, another on Thursday. Practical algorithm for DFT. Someone made a suggestion that we will go over cone-shaped orbitals. So it's not today, but it is next Tuesday. And observables, they are very important. We will cover them either in labs, in your talks, or maybe after the talk, because we need to rush through the material so that we have enough time for projects. Therefore, we are doing presentations on VASP skills a little earlier, because otherwise there will be no time for research. Like this. Okay. I see that Alisa wants to write an equation for us. With my help. Let's go to the board and write here the normalization of molecular orbital. So select some letter, phi sub I. And what do you recall when you hear the word normalization? Everything is normal, right?
Okay.
Everything is good. Help from class is appreciated.
It's like I can see it in my head, but I can't. I can't.
Normalization, orthogonality.
Okay, so like as far as the cross product.
Product. So you may multiply this function on itself. Just write this symbol once again. Yeah, maybe same argument.
Sure.
Same argument in the brackets are. Okay, and little star here. So what will you get if you integrate this product over all positions? Right, integral symbol here. And after that, d. So what are you going to get? If those are good orbitals.
I want to say density, but I'm not sure.
But density is before you integrate. This would be density. But after you integrate density of one electron over all space.
I don't know.
Yes, just guess.
Energy? I don't
No,
know.
no, no, no. When in high school, if you ever need to practice a little teaching in high school, design problems, you want easy grading for yourself. Right? If you are a teacher. And then you design all problems that they have answers like 0, 1, or infinity.
Okay, I'm gonna get one.
Right. Okay, thank you. So what is normalization? Integral equals 1.
Okay.
Right?
Got it.
Good. So, and what was here under the integral? It was density. So let's go rho sub I r dr. Right? Equals 1. What if right here rho 1 plus rho 2 plus rho homo make integral over dr. I think Alyssa did the hardest part. Can you? I did everything. I was so excited. you need to just put the answer.
You can watch our super senior mathematician at work.
Well, I've never actually done
Mathematician
this.
/
Yeah, right.
No preparation is needed, just
Are
common
you a
sense.
geologist?
So, I guess we can say.
Yes, excellent. But thanks, man. Good. So the stuff in here, summation of all occupied orbitals, we can call it total density. Right? So it's three-dimensional function. It's not multi-dimensional. It's three-dimensional. Right? But it carries information about all electrons, first, second, third, all which are all orbitals that are occupied. So this is density. Integration of a function gives one number, right? So when you speak about beginning of calculus and you have functions, it's a correlation between argument and function. If you do it as Excel table, one number as argument, one number as a function, 1 to 1. But if you have correspondence between a function with many numbers and a number, then you add the A, L at the end. functional. Okay, so common efforts of Elisa and London. I chosen you because you're so close to the edge, and it's easier for you to work here. You give an example of number of electrons function. Right? And if for density, it's also density functional for number of electrons. And the theory that we are learning is density functional of total energy. So the expression could be a little more complicated, like instead of integral rho total d r in the first power, it could be like to the power of 5/3, which is transfer. But it will not help us right now because this was done in the approximation that there are no ions. If you put in ions and electron interaction, the expression will be more complicated. But the idea is here. You take electron density, do some mathematical operation, and condense it into one default function. Okay? So when you are browsing in your Gaussian setup with like selecting D3 lib, can D3 lib, you are choosing the way how the density is converted into energy. There are like hundreds of different equations how this is done. You did it, right? Alyssa told that it is 1, and if you integrate this, it will be 1 plus 1 plus 1, as much as many number of electrons. But London did it in the head and gave us immediate event. AL. Okay. That's right. The attractor electrons. So it's time to start new. I don't know if I missed the slide that we are done with recall of old things and we are starting new things now. Okay, recall was 40 minutes. So our goal is to get total energy. And the theorem tells that if we do know the electron density, it immediately allows us to know so-called external potential. I need to define it. And it allows to know the total energy. So this is to some sort of corrupt logic. Before, we were designing Hamiltonian, including potentials the potential that exerted from ions to electrons, nuclear to electron interaction. And then we were solving for something derived from Schrödinger equation and getting total energy. Right now, we are moving in the opposite direction. We assume that if by some reason we already know total density, we can reconstruct this nuclear electron part of Hamiltonian, and we can reconstruct total energy. And since it is strange, we need to try our best to look through it. So the community of density functional theory used the word external for electron to nuclear interaction, because what is an opposite word to external? Internal. Internal, intrinsic. If I am electron, I'm internal to myself, and ions that attract me are external to me. Okay? So ions and anything else, like electromagnetic radiation or whatever, every outside influence on electrons is external. So instead of going this way, we are going opposite way. Do you know bad words?
Like degenerate?
I don't know. Degenerate is super bad. But if you do not like something, not in the aggressive fashion, but if you think that something is senseless, is not very intelligent, which words would you use? Feel free. You can erase things from recordings if they are too bad. Like idiotic, crazy, senseless. Any ideas about wrong, not very smart?
Boneheaded.
Boneheaded, okay. And there is a word, after we collect all bad words, I will ask you to translate into Latin. Or find such word that is also does exist in Latin. How do you say that something is completely senseless? You know this word. Even if you will not recall it in next seconds, you know. Let's play. Huh?
Irrelevant? Irrelevant?
One, two, three, four, five, six. Six words. Okay, let me help with last.
Stupid.
Huh? Stupid. Yes. Yes.
That's what I was thinking of too.
Any synonyms? Anything else? For stupid, it would be fine. Yes. Anything else that ends with D?
Can I buy a vowel?
Yes.
But I.
You can try another
You're a
one.
college student. You're before you bought it.
Huh?
Oh.
O? No.
E.
Hmm?
E.
Mm-mm.
Hey.
Yes.
There's gotta
We all thought that was gonna help. Is there an S?
Yes.
Okay.
Absurd.
Yes, correct. So you know this word. So if you start your derivations, your theories from wrong statement, you can tell that it is from absurd. Or if you speak in, if you're fluent in Latin, you like from and absurdum. So if you were taking formal logic or some math, there is a type of proofs of theorems ad absurdum. So if you make wrong statement and arrive to wrong statement that is evident, it is immediately means that you started from something wrong. Then what you guessed was not right, and anything opposite is correct. Make sense? Okay, at least we had a nice game. Fingerprint is a good word. So with our common sense, we know that source of electronic properties is ions. But in this theory, we are going logically in an opposite direction. But we can understand that density is a fingerprint of the crime guide of the positions of ions. And based on fingerprint, you can reconstruct where and which ion was sitting. Make sense? So it is like common sense understanding of the first theorem of Poinberger. Okay. So, and absurdum. We are going to guess that there is more than one correct total energies. Let me scroll back. I was feeling very uncomfortable reading this material and delivering it several. So the idea is that if you have one correct total energy, you will get one correct total density, you will get one correct total energy. So one, only one, or I don't like this precise formulations in math problem. Sometimes they are needed. And right now we are going to suggest that if these arrows are not perfect logically, that one can get more than one correct total energies. The system has two total energies which both are correct. No one forbids us to guess. Starting from density, we'll get more than one correct total energies. And then we will try to wrap up this statement into the logic, and we will obtain that it will get us to nonsense in mathematical meaning. And then the idea we will realize that it was a wrong thing to do. And it will be sufficient proof that if you know correct density, there will be one and only one total energy that found based on it. Okay? We are not going to do research in the space of theorems. It's just a quick overview so that we know what is being said in community and why people believe in this. Believe is not the right word. Why everyone agrees that it is proved to be correct. So we will start that there is a more than one total energies. So it will be total energy A and total energy B. And then through mathematical manipulations, we will get that EA plus EB is bigger than EB plus EA. Not bigger or equal, bigger. And it will be a sufficient argument to tell that no, there is only one. There cannot be two. What's the name of the movie when people look at section, then there is a lightning, and there should be only one?
Oh, Highlander?
Highlander, yes. So there should be only one. So we are going to use one of the components of our previous discussion, the variation theorem. So that if we perturb the ideal wave function that gives minimum energy, then expectation value of Hamiltonian will give energy bigger than minimum, right? That's what will be used for deriving Carter-Fox theorem. So our main statement is that from density you are getting the external potential. And in our proof, we will expand our hypothesis, not just different total energy. We will tell that there are two branches of external potential. This is a very absurd statement, as we will see later, because it means that for one total density, we can, from one fingerprint, we can reconstruct two criminals. So from one density, we can reconstruct different modes, which will be wrong. But right now, it is wrong only for our common sense. We haven't arrived to this conclusion, and we need to do some logical manipulations. There is a high chance that you will never need to reproduce it in your life. So it is only for your curiosity. So there are some logical manipulations that show that this statement will be wrong, and therefore we will cancel our initial statement and tell that there is only one external potential and only one total energy. Okay. So let's suppose that we do have minimum of total energy for wave function psi sub a. Then, if we will assume that there is some other wave function psi sub b, it will be psi sub a plus something. Therefore, if we find the expectation value of Hamiltonian corresponding to ideal system A with ideal wave function A, we will equals E. Now I'm adding psi A plus something. Something. This should be bigger than E sub A because of the variational theorem. Okay? It's all our story about minimization. Well, not minimization of geometry, but going self-consistency cycles and finding the minimum of total energy. We go through equations. If you are at right wave function, we get a E. If you have the wrong wave function, we getting bigger energy. Okay? And we can tell that psi sub b is our wrong wave function. Because we have one minimum. And everything, as far as we deviate, it will be different. So it is shown here. Expectation value of Hamiltonian A with wave function psi b is bigger than our ideal energy. So next step in this logic is a nominal step. It's just add and subtract another Hamiltonian to which psi sub b will be eigenstate. Right? We are not violating any rules. We can add and subtract if there are two equal terms. We can always add and subtract them anywhere. Okay. If we do this and open the brackets, then this minus part will go to expectation value of Hamiltonian B is for wave function B. And here will be expectation value for difference of two Hamiltonians. One is Hamiltonian that we believe is correct, and H sub b is just Hamiltonian for which H sub b will be eigenstate. So we subtract these two Hamiltonians, and we keep the bigger sign, or piece of a smaller, from the which theorem? How do you call the theorem?
The variation.
Yes, variational theorem. Now, we are going to open. Oh, I'm cheating. I'm supposed to write it myself, but then it will be very, very long. So I'm just showing. I do not support this style. Ideally, instructor should write everything. So we can open this expression of subtraction of two Hamiltonians in a very formal sense. I'm not going to switch on my CPU. I'm not going to think. I'm going to just plug in based on definitions. So definition is that any Hamiltonian is a summation of kinetic energy, electron-electron interaction, and electron to nuclear attraction, right? Which is called external potential in the community of density function. So if it is Hamiltonian A, kinetic energy is the same, electron and electron interaction is the same, but the external potential which accumulates positions of ions will be external potentials for system A. If it is system B, the kinetic energy and electron interaction will be the same, as long as we have the same number of electrons. The only difference is external potential, what is defined by positions of ions in mole. So if we subtract two Hamiltonians, it will be subtraction of two external potentials. Basically, subtract potentials for molecule A and molecule B if there are two different molecules that are reconstructed from single density. So difference of Hamiltonians is equal just difference in external potentials. Okay, we can plug it into the inequality that was taken from variational theorem. So here is E sub A, energy that we believe is correct, minimal. E sub B, energy that we assume is larger and wrong. And the expectation value of difference between external potentials of two molecules that we generated out of density. Now, Alicia, you can sit there. I'm not going to invite you once again here. You already worked hard to help all of us, but I will use your help. So, Alyssa taught us that multiplying wave function on itself with this little star and just multiplying on itself, it is density, right? Or absolute values. So when we open this expectation value, we will see that potentials are local. They do not contain derivatives. Therefore, we can move wave function from here to there and just multiply product of wave functions, which is density, by difference of external potential. Right? And product of wave functions is density. Density for system B. It's already, well, I'm not thinking, otherwise I will become crazy. This imaginary system B that we was our second branch of reconstruction from okay, and now it's time to rewrite the inequality once again. Energy A, energy B, one is smaller than another one, plus difference in the potentials, external potentials multiplied by density B. So you can write this as So I do not know Latin, and I have doubts. Add means from or to. So we are going from absurd or we are going to absurd. But something absurdic is definitely here. So let's take this expression and think back about our original guess that from one density one can reconstruct, generate two external potentials, two molecules, two total energies. If this was correct, there is no limit on which we call A and which we call B. So if you just swap indices, our logic shouldn't suffer. We didn't told which one is first, which is second. So we take this expression and swap indices. Wherever we had A, we write B. Wherever we had B, we write A. So density A and difference of external potentials and energy. Now here will be energy A. So we are going to take these two expressions, one with straightforward sequence of indices and another with swapped sequence of indices, and compare them. So we'll just no, do not believe it. Do not believe it. I just want to remove the too much of notations so that we okay, so we do have two branches, and we did set them up in the same way. They differ just by the order of indices. One is A, another is B. So another logical input. At the original formulation of the input for theorem, we assumed that there is only one density. We know it for sure. We have branches for external potentials, for total energies, but density is one. Therefore, density for A and for B should be the same. Okay? So we remove indices. Remove indexes here, and it will be just density. Okay? What will be the next step?
Add the inequalities.
Yes, adding them together. So if you add together these inequalities, here you have B with sign minus, here you have B with sign plus. Here you have A with sign plus, here you have A with sign minus. What will happen if you add together?
They cancel out.
Yes, so everything, this integral will cancel out, right? And then on the left, you will get E sub A plus E sub B smaller than E sub B plus E sub A. Okay? For everyday common sense, I don't care who is bigger than what. But for math, it is a big crime. Like it is either equal or non-equal. And here we have these same things on the left and right, and through our logical steps, we got that it is inequality. So we got the statement that is definitely wrong. And all our logical steps were correct. At least for you, because you didn't quote me replying. And at least for me, because I didn't quote line the authors of the theory. So the only way of the wrong answer is that original statement. And the original statement was that from one density, one can get two branches of potentials and two total energies. No. If you assume this, we get nonsense. Therefore, from one density, you can get one and only one external potential and total energy. This is really impressive achievement. It means that we were wasting time thinking about multi-electron wave functions. If one can find total energy, if one can find external potentials, it means one can reconstruct any property of molecule just based on the density, just based on the distribution of charge density, not the wave functions, not multi-dimensional things. So this parameterized by 3 Cartesian projections density is sufficient to find any properties of molecule if the theorem is right. And we logically found that it is right. It means that we can live an easy life. Just find correct function and enjoy it. So wrong statement was that same charge density leads to alternative branches of observables. It is wrong. Only one branch of observables. And I'm not going to reproduce proof here. You've already heard it. We just started so that from one density, you get one external potential. And through absurd conclusion, the guess that there are 2 different branches is wrong. Therefore, the final proof is assumed complete. One density, one external potential. And you already discussed the fingerprint, right? So for criminalists or criminal police, it would be a good theory telling that single fingerprint corresponds to only a single person. I'm not sure if a theorem exists about fingerprints, but for densities and external potentials, it does exist. One density, one external potential. Next time, we will discuss other multiple functionals. You know that in your Gaussian software, you can shop for loop, 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 TB, and there is a theorem telling there's only one correct. All others are wrong, but they're just wrong in a different measure. Okay, thank you for your questions. I look forward to see you on Wednesday night for practical steps. And if you are doing research, then we will have a meeting at 4. Okay. I will be happy to collect homeworks if you are Done with it? You
I mean,
part
this is like where I'm at, so
It's better,
I might
it's
as well-
better.
I can
Okay.
email it to you, I'm alright.
Okay. Anyone else want to brag his homework achievements? I should design something like points of timely submitted are multiplied by 3.